An electrical network theorem is a tool that is widely used to solve complex electrical problems. It was named after electrical engineering professor Jacob Millman, who developed it. Millmans theorem is based on Thevenin's and Norton's theorem and is very effective in simplifying complex electrical circuits. Millmans theorem, also known as the parallel generator theorem, is important for calculating voltage across the load and current through the load. There are two ways to use Millmans theorem. It can be applied to circuits containing voltage sources alone or a mixture of voltage and current sources. In electrical engineering, Millmans theorem or the parallel generator theorem is a method to simplify the solution of a circuit. Specifically, Millmans theorem is used to compute the voltage at the ends of a circuit made up of only branches in parallel. It is named after Jacob Millman, who proved the theorem. An electrical network theorem is a tool that is widely used to solve complex electrical problems. It was named after electrical engineering professor Jacob Millman, who developed it. Millmans theorem is based on Thevenin's and Norton's theorem and is very effective in simplifying complex electrical circuits. Millmans theorem, also known as the parallel generator theorem, is important for calculating voltage across the load and current through the load. There are two ways to use Millmans theorem. It can be applied to circuits containing voltage sources alone or a mixture of voltage and current sources. What is Millmans theorem? This method allows us to determine the voltage across parallel branches of the network. When several sources are connected, this method reduces the complexity of the network. Millmans theorem statement: a circuit with parallel voltage sources and internal resistance can replace one equivalent voltage source connected in series with an equivalent resistance. We will look into it with a diagrammatic approach. The complex circuit arrangement in Fig can be reduced to a simple network circuit. For circuit analysis, there are different types of network theorems available. In that, Millmans theorem is one of the most useful methods for particularly electrical circuits which contain many voltage sources. Based on this theorem, each voltage source as well as their particular resistors generates a current, and the amount of all currents is equivalent to the whole current generated through the circuit. The formation of Millman circuits can be done through resistors and there is no involvement of reactance. The circuit's whole output voltage can be stated through Millman's theorem that can be stated through the first Ohm's law. Here, to analyze Millman's equivalent circuit, the load should be disabled. Similarly, to find the resistance of the Millman equivalent circuit, the voltage sources must be changed with short circuits. This article discusses an overview of Millman's theorem with examples. Steps for applying Millman's theorem. Following certain simple steps, we can summarize the application of the theorem to a valid electrical network. The steps are listed. Step 1. The circuit converts all voltage sources to current by dividing their potential by their internal resistance, where G represents the conductance of the circuit. Limitations of Millman's theorem. Despite the generic nature of Millman's theorem, the application of the theorem is restrained by some conditions, and it does not apply to every circuit. The conditions which need to be satisfied for the application of the theorem are: Millman's theorem does not cover circuits with impedances among independent sources. Millman's theorem does not apply to circuits where dependent sources complement independent sources. There is no application of this theorem when two independent sources exist in the circuit. Determining the direction of current. The current direction across each resistor is determined by the polarity across the resistor itself, rather than the polarity across each battery. It is possible for the current to be forced back through a battery. It is crucial to remember this because Millman's theorem does not offer as clear an indication of an incorrect current direction compared to the branch current or mesh current methods. It is necessary to closely consider the polarities of resistor voltage drops, as determined by Kirchhoff's voltage law, in order to determine the direction of currents accurately. Advantages and applications of Millman's theorem. Millman's theorem can be used to simplify a complex network. Some common advantages and applications of the theorem are listed below. Millman's theorem changes voltage sources into current sources and vice versa in circuits with voltage and current sources. Millman's theorem can be applied to determine the voltage across a set of parallel branches when sufficient voltage sources are present to prevent a solution based on the series parallel reduction method. Millman's theorem is elementary to utilize because it doesn't need the utilization of instantaneous equations. Typical applications include circuits whose topology is complex, using many op-amps. One method of deriving Millman's theorem starts by converting all the branches to current sources, which can be done using Norton's theorem. A branch that is already a current source is simply not converted. In the expression above, this is equivalent to replacing the term in the numerator of the expression above with the current of the current generator, where the kth branch is the branch with the current generator. The parallel conductance of the current source is added to the denominator as for the series conductance of the voltage sources. An ideal current source has zero conductance, infinite resistance, and so adds nothing to the denominator. Ideal voltage sources. If one of the branches is an ideal voltage source, Millman's theorem cannot be used, but in this case the solution is trivial. The voltage at the output is forced to the voltage of the ideal voltage source. The theorem does not work with ideal voltage sources because such sources have zero resistance, infinite conductance, so the summation of both the numerator and denominator are infinite and the result is indeterminate. Millman's theorem in network theory states that in a network with multiple parallel branches, the voltage across each branch is equal to the ratio of the sum of individual branch currents multiplied by their respective resistances, divided by the sum of all branch resistances. This theorem simplifies complex electrical networks. It represents such networks as equivalent circuits with simpler voltage sources and resistors. Applications of Millman's theorem. Millman's theorem is widely used in electrical engineering for a range of applications. The applications of Millman's theorem encompass the following: circuit analysis and design. Millman's theorem enables engineers to simplify complex electrical circuits with multiple parallel branches, making it easier to analyze and design circuits. It helps determine voltage and current distributions, power dissipation, and overall circuit behavior. Power systems. Millman's theorem plays a crucial role in analyzing and designing power distribution networks. It aids in calculating voltages and currents at different nodes, assessing power flow, and determining the performance of power systems. Electronic circuit design. When designing electronic circuits with multiple parallel branches, Millman's theorem helps simplify the circuit and analyze voltage and current characteristics. It assists in optimizing circuit performance and ensuring proper functionality. Control systems. Millman's theorem is utilized in the analysis and design of control systems, allowing engineers to understand and manipulate voltage and current parameters in parallel branches. This aids in the design of stable and efficient control systems. Telecommunications. In telecommunications systems, Millman's theorem is employed to analyze and optimize network configurations. It helps assess voltage and current distributions in parallel branches, ensuring reliable transmission and reception of signals. Millman's theorem importance. The importance of Millman's theorem extends to various applications in electrical engineering. It helps engineers to analyze and design circuits. It is used in power systems, telecommunications, control systems, and electronic devices. It helps in checking the performance of circuits. It also helps in calculating the voltage and current distribution. Millman's theorem can also help in determining power dissipation. Advantages of Millman's theorem. Millman's theorem offers several advantages that make it a valuable tool in electrical engineering, simplifies complex circuits. Millman's theorem in network theory allows for the simplification of complex electrical networks with multiple parallel branches. By representing them as equivalent circuits with voltage sources and resistors, it simplifies the analysis process and reduces complexity. Facilitates circuit analysis. The theorem provides a systematic approach to analyze circuit behavior, including voltage drops, current flows, and power dissipation. It helps engineers gain a better understanding of the circuit's performance and characteristics. Saves time and effort. By simplifying complex circuits, Millman's theorem saves time and effort in analyzing and designing electrical networks. It streamlines the calculations required for circuit analysis, enabling engineers to focus on specific components or branches without losing accuracy. Versatile application. Millman's theorem can be applied to a wide range of electrical circuits, including power systems, control systems, telecommunications, and electronic design. Its versatility makes it a valuable tool in various fields of electrical engineering. Accurate results. When applied correctly, Millman's theorem provides accurate results in analyzing circuit voltages and currents. It helps engineers make informed decisions in circuit design and optimization. Enhances understanding. By simplifying complex circuits and providing a clear representation, Millman's theorem enhances engineers' understanding of circuit behavior. It allows for better troubleshooting, optimization, and overall circuit comprehension.